Okay, so welcome you all to the Brazilian Algebraic Geometry Seminar. So it's a pleasure today to have Maral Mostafazadehfard from the Federal University of Rio de Janeiro. And she's going to talk on the divisor class group of Hankel determinantal rings. So please, Maral.
Yeah, thank you, Eduardo. Thank you, all of you organizers, for the invitation. Actually, the theme of the talk of today is about the divisor class group of Hankel determinantal rings. I have chosen this theme because I was thinking maybe this theme is closer to the interest of the geometers. So I hope you enjoyed the talk. So this work actually is a joint work with Aldo Conca and Matteo Varbaro from the University of Genova and Anurag Singh from the Utah University. This work it has been published already in 2018. And the plan of the talk, I will start from the definitions, examples, and the simple introductions. The first 20 minutes would be a review of some well-known classical results, and we will see very slow seminars, and after that, in the next 20 minutes, I'm gonna start talking about the results, and the talk will get acceleration. So after that, I'm gonna talk about our contributions, the results, and the questions that is still open. So let me start from the definitions of Hankel determinantal rings. When we are talking about the Hankel matrices, actually we are talking about a matrix of indeterminates such that this matrix is anti-diagonal. What does it mean? It means that all of the indeterminates on the anti-diagonal of this matrix is a fixed indeterminate. So when we are talking about the Hankel determinantal rings, we mean a quotient rings of the quotient of the polynomial rings in terms of these indeterminates over the ideal generated by all minors of size T of this matrix. So you can think about this ring as a homogeneous chord ring of higher order secant varieties of rational normal curves. So if you let me, I just gonna do a review of the importance of the rational normal curve. Suppose that we are in the plane case, so the standard conic in P2 actually is xz minus y2 as the image of the map given by this parameterization. This is a Veronese map, Veronese embedding actually. And when you're thinking about in a higher dimension, so we can define this curve as the image of this Veronese map. So as it is embedding of from P1, so we know that we have an isomorphisms between P1 and C. So this called the standard rational normal curve. So we know that it is famous that it is a smooth of genus 0, irreducible curve of time 1. And if you look at the generators of the image SR, SR minus 1T, etc., you can see that they are all linearly independent. So it means that this curve is non-degenerate or such that this curve is not contained in any hyperplane. But if you look at the intersection of this curve with the general hyperplane, you can see that this intersection has exactly R intersection points. So the degree of this curve is exactly R. So I am emphasizing these properties because of this fact that actually any irreducible non-degenerate curve of degree R in PR is a rational normal curve in PR. So irreducibility non-degenerate ones are not very expensive hypotheses, but so as far as you keep the degree equal to the dimension of the projective space, so you are actually working with a rational normal curve up to a linear transformation. So, let's talk about the algebraic counterpart of this curve. you can consider the homomorphisms between the polynomial rings to the domain of K of S and T, sending xi to SR minus ITI. So the rational normal curve actually is, has defining ideals coming from the kernel of this map. So, and you can think about it as an minors coming from the Hankel matrices of size 2 by R. And so when you're talking about the coordinate ring, so you can consider actually this is a Hankel determinantal ring with this size. In general, if you consider that we have a domain parameterized, the parameterization is given in this sense that the u1 ut minus 1 v1 vt minus 1, just consider hi in this sense, in this form. So again, we can define homomorphisms from the polynomial rings to this domain S, sending xi to hi minus 1. So if you keep in your mind what was the parameterization, actually the kernel of this map is a defining ideal of the second varieties, or we say that the kernel of this map actually are exactly the minors, size T minors of Hankel matrices in this form here of size T by N. So you can think about this quotient ring as a coordinate ring of the T minus second varieties of rational normal curve in Pn plus 2 minus 2. N plus T minus 2. So, for example, the first secant coming from the all 3 by 3 minors of Hankel matrices of size T by N. And when you're talking about the second variety, it is coming from all of the 4 by 4 minors of the Hankel matrices. So, and we can go ahead in this sense. So, these rings actually have very nice properties that I'm gonna introduce some of them here. These are actually would be the well-known properties. So again, consider this matrix and the quotient ring, which is the Hankel determinantal rings. The first property that I would like to talk is about the properties that consider the some property that I say it is an elasticity property of this matrix. So what does it mean? It means that when you're working with this with the minors of this matrix, you just keep in mind what is the size of the minors and what are the number of the indeterminates. And the size of the matrix is not doesn't matter. You can forget about the size of the matrix. So this gives you this ability, the ability that always you can work with the maximal size minors. And it's a good property because when you can consider just the maximal minors, we know that the Egon-Norskott complex will give us the minimal Fourier resolutions of these kind of ideals. We get lots of good properties, for example. So they are Cohen-Macaulay. This result for the first time was published by Gruson and Peskin in 1982, but after that by other mathematicians was reobtained, for example, Eisenbach, Conca, Zareh-Nahandi, etc. But for the first time, it was done by Gruson and Peskin. Gruson passed away in April as a victim of the COVID-19. Let me go on, and you can think about the Hankel determinantal rings as a second variety of higher order second varieties of rational normal curves, but sometimes you can consider this matrix actually as linear specializations of the generic matrices. So what we get is that actually the dimension of this ring is 2t minus 2, and so the codim of the determinantal ideal in terms of the size of the matrix is this number. And moreover, we have the homogeneous system of parameters of these rings that actually they are linear regular sequences of R. It's given by this indeterminates, and the complement set of this indeterminates actually is giving us the circle of this ring. So the circle of this ring is generated by the monomials of degree t, and so the invariant of the rings is this negative number 1 minus t. There are lots of other nice properties. For example, this is well known, the multiplicity of these rings is n choose t minus 1, and the singular locus also, it is well known what is the singular locus, which is coming from the one less size minors of these matrices. And at the end, okay, these rings are set theoretic complete intersection. This is work due to Walla. Actually, he explicitly explained what are the generators of these ideas up to a radical. And as I have learned from Aaron, it is actually, they are exactly coordinate-wise sections of the same matrix of the Hankel matrices. So these were all very nice properties of Hankel determinantal rings, but we couldn't find any anything about the divisor class groups of these rings. They were Cohen-Macaulay normal domain, so it can be defined the divisor class group for these kind of rings and determine what are them. So let me start from very simple introduction to the divisor class group, and after that I'm gonna talk about our approach. Divisor class group actually can be defined for any Kuru ring, and the Kuru ring have some properties. For example, we have a minimal family, minimal defining family of Kuru rings in based on the discrete valuation rings here, A localized at P, when P actually coming from the all codimension 1 prime varieties or prime ideals. We can define, we know that the Veil divisors actually are all prime ideals of codim 1 are Veil divisors. So we can define a group which is consisting of all formal sum of the codim 1 prime ideals, where the coefficients coming from the integers, and this sum is actually a finite sum. So if you consider a group homomorphisms from the fraction field of the Krull domain A, this K star, to this group, we define this group homomorphism actually by the normalized valuations coming from the discrete valuations A localized at P's. So the co-care of this group homomorphisms actually define the divisor class group. So you can consider all the divisors modulo all of the principal ones. So it will give us the divisor class group. And when we are working actually in the ring is when we have a ring normal domain ring. And we know that all the Noetherian normal domain are Kuru rings. So in this sense, when we are working with the ideals, we say that an ideal of a ring actually is a divisorial ideal, if and only if it can be written as the intersection of the symbolic powers of primes of height 1. And in this sense, we define the divisor class of I as this formal sum that the coefficients coming from the symbolic power of the class of Pi. So, and if I want to recall you what is the definition of the symbolic power, you can consider that all of the elements of R that up to a regular element, up to multiplication by a regular element, they belongs to the same ordinary power of the prime P. So let's go on And for us, for Hankel determinantal rings, that we had these properties that they are Cohen-Macaulay domain, and by the results of Watanabe, they satisfy the third conditions R1, but not R2, but R1 is sufficient for us. So they are Noetherian normal domain, actually, they are Kuru rings. So that it was a very natural question that what is the divisor class group of Hankel determinantal rings? And actually, the divisor class group of other kind of determinantal rings were established before. For example, if you consider the determinantal rings, I mean the determinantal rings coming from the generic matrices, where we have all indeterminate xij's, and consider the ring S as the quotient of this polynomial rings over the all t-sized minors of the generic matrices. Also, they are satisfying the conditions of R2, and Egon Huckester has shown that actually they are Cohen-Macaulay domain, so they are a Noetherian normal domain, they are co-ring, and Bruns actually determined the divisor class group of this quotient ring, which is the integer numbers. And these rings are exactly Gorenstein when they are a square. They are actually the quotient of the square matrices when you are just have quotient over determinant. So it was nice. So, and as you can see, the divisor class group in these rings doesn't depend on the size of the minors and the size of the matrix. It is independent. And how about the generic symmetric matrices? If you consider the generic symmetric matrices, again, by results of cuts, we know that they are normal Cohen-Macaulay domain, so they are cool ring. And Goto actually established the divisor class group of these rings, and it is isomorphisms with, say, 2. And the Gorenstein property just occurs when the size of the minors and the size of the matrix have the same parity. And again, the divisor class group doesn't depend on the size of the minors and on the size of the matrix. And for the skew symmetric matrices or alternating matrices, again, it was a result of Klepp and Luxev that Pfaffian of these matrices for even size, it is even, is a normal Cohen-Macaulay domain, and again we have a cool ring, and Avramov actually 1 year before has shown that they are a unique factorization domain. So it is already the divisor class group is 0, and you know, it's famous that the divisor class group is determining the property of the UFD, and by the result of Morty, of course, they are always garnished. So, but what about the Hankel determinantal rings? So again, here the divisor class group is 0, so it doesn't depend on the size of the matrix or size of the minors that you are considering. And okay, for divisor class group of Hankel matrices, let me introduce you some notations. First, consider that we have a Hankel determinant, Hankel matrix of size t by n, and just consider the first t minus 1 rows. So what we are doing that actually we are omitting the last row and consider the first t minus 1 columns. So we have 2 submatrices of the Hankel matrices that the maximal minors of them are defining 2 ideals, P and Q. So if you keep in mind what was them, what are them, you can continue in this setting. So actually P is the minors of a Hankel matrix of size t minus 1 by n. And if you continue in this sense that omitting the last column and consider the ideal which is generated by the other part of the matrix, and we denote it by P, and I say fake power 2. And I explain that why I am saying that fake power. It is just a symbol. So it is obtaining by omitting the last column. And if you go on in the same way and doing in the same way, we omit the two last one columns and we call it the P fake power 3. So we're going to show that actually the codimension of P is 1. If you remember this one is the ideal P defining by this minors of the submatrix of Hankel. So we can show that actually these fake powers are exactly the symbolic power of P, and actually the canonical ideal or canonical module here are exactly the second symbolic power of P. And the divisor class group of the Hankel determinantal rings is generated by the class of P, and the order of this element, or I mean the power of P, the symbolic power of P, which is the principal, is exactly n minus t plus 2. So the divisor class group of the Hankel matrices is a cyclic, is a finite cyclic of order n minus t plus 2. And as you can see here, the divisor class group depends on the size of the minors and depends on the size of the matrix. And as you can see, these rings are never factorial if you change the t over m. And even in the case of Q-Gorenstein, I mean when t is equal to n, and when you are working with the hypersurfaces, the divisor class group will be Z2. So even the Q-Gorenstein case, they are not factorial. And obviously from the order of this divisor class group, the order of the canonical divisor would be the same number or the half of that. So we have a finite divisor class group. So in this group, the canonical divisor has finite order, or such that we can say that the canonical divisor is a torsion element of a divisor class group. So in this sense, we say that actually our ring is Q-Gorenstein. So it is a specific property of them. If we want to review the approach of the proof, the ingredients of the proof, just let me tell you some ideas. We started from the codimension 1 prime ideal P, and we considered the discrete valuation ring of R localized at P. And with the valuation coming from this fraction field of R localized at P to Z, defining over the all minors by row indices 1 to t minus 1 and the column indices I1 and IT minus 1. So we define this valuation in this sense, n plus 1 minus the last index of column. Okay, so in a sense, for this divisor discrete valuation ring, actually the last t minus 1 binaries coming from the ideal P is the uniformizing elements. So all the symbolic powers actually are principal and coming from the ice power of P. And in this sense, when we consider the valuation of the elements coming from the fake powers, so we understood that, okay, the fake powers must be contained in the symbolic power, and at the localization, they are equal. So, but exactly here was a difficult part for us to show that actually these fake powers are exactly the symbolic powers. For showing this, we need to show that actually these fake powers are unmixed R module. If we could show that, so we could get the equality. But after some lemmas and some difficulty, we could show even better. We could show that actually these fake powers are Cohen-Macaulay. much better than the unmixed one. And so by the Cohen-Macaulay property, we get equality between the symbolic power and these fake powers. And also, in particular, we get that they are reflexive R module. But how about the, so up to now, we could show that these are equal. And after that, we think about the divisor class group. For the divisor class group, just regarding this delta coming from the first t minus 1 minors, so this would be our delta. And there's a good property for the Hankel determinantal rings that are localized at delta actually is a polynomial ring. And the only prime ideals of height 1 that can cut delta is exactly P. So the main idea was using the Nakata theorem. So by Nakata theorem, we knew that, okay, the divisor class group actually is the kernel of the canonical map from the divisor class group of R to the divisor class group of the localization. So the kernel was generating by the class of P. So the divisor class group was generating by P. Okay. And as a corollary, let's think about the simplest case of Hankel determinantal rings, which are rational normal curves. For the rational normal curves, it was well known what was the divisor class group, but we can use our general results for this well-known fact and just recover it. Okay, how we think about that? We consider the 2 by 2 minors of the simple Hankel matrix XZ, and so we are in a 3 affine space. We have a quadratic cone xy minus z2. If you consider the p, which is equal to x and z, this is a veil divisor. It is of codyne 1, but it's not the principal ideal. But the second symbolic power of p actually is principal. And so the divisor class group is the order of p, it is z2. So you can look at this cone and you can look at this line over this cone as a line of p as a veil divisor here. But in general case, if you consider that rational normal curves coming from the 2 by 2 minors of the Hankel of size 2 by n, so you can consider the quotient ring here, which is the coordinate ring of this rational normal curves. Here, P is the veil divisors coming from the x0 to xn minus 1. The codimension of P is 1. And Pn's power is exactly principal. This is a symbolic power of P, which is generated by x0, and none of the lower symbolic powers are principal. This is the first place that it's occurred. And actually, the divisor class group of R is exactly Z over NZ. Okay, but we obtained another result that and they encourages us to ask another questions. For example, we could compute the multiplicity of all of the symbolic powers of P, and in particular the multiplicity of the canonical divisor. And moreover, we could show that actually all of these elements of divisor class groups are maximal Cohen-Macaulay R modules of rank 1. And if someone is interested to the Ulrich modules, and if someone wants to know, among all divisors in divisor class groups, we just have one of them, which is the Ulrich module. Roughly speaking, Ulrich modules means that the minimal number of generators of a maximal Cohen-Macaulay modules is exactly equal to the multiplicity. So, and the other result that was very promising actually was that the Hankel determinantal rings has rational singularities, and our method was reduction modulo P methods, and we study these rings in the characteristic P. And what we have shown really is that we have shown that these rings are F-rational. So for sufficiently large P, sufficiently large prime numbers P, what does it mean? It means that for any prime numbers which are bigger than or equal to the size of the minors. So these rings are F-rational, so they are F-rational types. And we have used the theorem of Smith, which is saying that, okay, F-rational type rings have rational singularities in characteristic 0. So, good. We have Q-Gorenstein rings with rational singularities, and all of the elements of divisor class groups are Maximal Cohen-Macaulay matrix. But actually, if you have a Q-Gorenstein rings with rational singularities, it need not be true that all of the divisor class groups be Maximal Cohen-Macaulay. There are examples that they are not. So we have a better property. So it encourages us that, oh, maybe we can say better than rational singularities. Maybe they have a better properties. For example, if we look at the F-regular rings, if someone is familiar to F-regular, so for the F-regular rings, this property of these rings that all of the divisor class groups elements which has finite orders are Maximal Cohen-Macaulay. So maybe the Hankel determinantal rings are F-regular. This actually, the F-regularity means F is the first letter of the Frobenius. So it means that the singularities that comes from the Frobenius map. And if we want to think in the geometry, in the algebraic geometry sense, if I'm gonna to give you some idea, we can consider the theorem of the Watanabe in characteristic 0. He's saying that when we have a Q-Gorenstein rings, so the notion of F-regular type is equivalent to the notion of log terminal singularities. So if we could show that, okay, actually the rings of the Hankel determinantal rings are F-regular, so this property is substantially stronger than rational singularities. But by now, we have just partially answered to this question. If you consider that R as a Hankel determinantal rings in characteristic P, we know that in the case of the hypersurfaces, they are F-regular. It is easy to show that, okay, R actually for the rational normal curves, they are also F-regular. It's easy to see, to explain. And when we are working with the size of 3 by 3 minors, or I mean the first second variety of rational normal curves also are F-regular. But for higher second variety, for the second variety and higher, it is so open for us. Okay, if you want to face to this problem, that consider the F-regularity, there are lots of methods that you can deal with. Sometimes the idea is that, okay, for example, for the case of the hypersurfaces, this is the case that the ring actually is Gorenstein. And we know that the notion of the rational singularity and the log terminal singularity in the Gorenstein case are the same, they're equivalent. So, okay, for t is equal to n, we can say that, okay, we had it because we have shown that they are they have rational singularities. So, in the Gorenstein case, they are F-regular. But for the other cases, you can have some approaches. For example, think about the anticanonical cyclic covers, or maybe you can think about the F signature to show that this is positive, or another ways. But there is another way that you can think about the F-regularity, but it is very stronger than showing that F-regularity. You can think about the actually invariant rings. Are they invariant rings of action on a group, linearly reductive classical groups over polynomial rings? If you can show this, actually you have shown that something very stronger than F-regular rings. Why we are thinking this way? Because when you look at the results that are in the literature about the generic determinantal ideals, so actually they are invariant rings of an action of the linear reductive groups over polynomial rings. In a better sense, this G actually here is the GL of T minus 1 of K. Suppose that, yeah, the size of the matrix is n by n. Anyway, if you look at the generic symmetric matrices and you look at these rings also are invariant rings of an action of orthogonal groups over the polynomial rings. So they are pure subrings actually of polynomial rings. And by Bototop's theorem, we know that, okay, all of them has rational singularities, and we can go further and think about these Q-symmetric matrices and Pfaffian of the even order 2T. So again, they are also an invariant ring of polynomial ring acting by the symplectic groups. 2T minus 2, all of them are reductive groups. But okay, let's think about the Hankel determinantal rings are. So what is the invariant ring? Are they really invariant rings of an action of the group over the polynomial ring? This is a mysterious point for us and we don't know. But if one could show this actually, so the F-regularity would be a corollary. But we know that there exist F-regular rings, that they are not invariant rings of an action of any linear reductive classical groups over polynomial rings. So it's really mysterious. Maybe they are invariant rings or maybe they are not. But if you are interested to show that maybe they are not, so it's better to think about the some local cohomology modules. But if you want to show that, yeah, they are actually the invariant rings, so you should get another approach. Okay, thank you. I'm gonna stop here.
Okay, thank you, Maral. Are there questions? I have one question at least, Maral. Have you checked, I mean, it's a very intriguing question, the last one you made about the determinantal ring being an invariant ring. Have you checked it for smaller cases of T and N?
Yeah, actually, but I have no idea actually.
Okay, so you don't know the answer to the question even in the smaller cases?
No, even in the smaller case, I have no idea. So
Okay, okay, right.
maybe they are, maybe because if we are very suspected, maybe they are not.
Okay,
We
I
are
see.
not sure. We have some feeling that maybe they are not invariant
Right.
ring, but
Okay.
maybe they are because
Okay.
lots of determinants are ignoring that.
Right. Another question was that, I mean, all of the rings that you consider, they are coordinate rings of projective varieties, right?
Yes,
Can
they
you
are
say something about the divisor class group of the projective variety?
No. You know, there is a difference. Actually, we are just working with the affine case. In the affine case, it's a bit different. For example, for us, the polynomial ring, for example, the coordinate ring of the projective varieties could be K of x0, x6. and these rings for us is factorial ring.
Mhm.
So in the affine case, we say that the divisor class group of this ring is 0. But when you consider it as a projective space, it is Z.
Mhm, right, yeah. It's,
So
uh-huh.
in the perspectives, it could be different. Even I think that the rational normal curves, if you consider it in the affine case or if you consider it in projective case, it's different.
Right. And have you considered the rings of other kind of varieties? For instance, you talked about the rational normal curve, right? But at least we have seen a talk about the secant varieties of these Veronese-Segre embeddings by Rick, right? And
Yes.
can you do something for them as well?
Usually, I haven't
Right,
thought
yeah.
about it, but usually the main tool to study the divisor class group is the Nagata theorem, and the crucial part is that you try to find an element that by localization that element you get a factorial ring. So if you get a factorial ring, you get a divisor class group is equal to 0. So what we find your divisor class group would be the kernel of a map. So the main method, even for the other determinantal rings, is almost this. But I haven't studied the other varieties, but it could be interesting. Yeah,
Yeah, it would be interesting. Yes.
Yeah, it would be really interesting.
Okay, interesting. All right. Are there questions? More questions? So if not, I'll ask you to thank Maral again.